Well, hey there, and welcome to our lesson on volume of spheres. And we're going to actually touch on the surface area of a sphere as well in this lesson. So let's start out by making sure we understand exactly what it is we're dealing with when we talk about a sphere. You may recall from our time with circles that we said a circle is the set of all points in a plane that are equidistant from a given point. So, here's our given point, and if we go out a set distance, um, from that point, we come across uh, all these points right here in a plane, meaning it's flat, that are equidistant from that point. Well, a sphere is almost the same definition, but if you look it over, you'll notice that one word has changed. And the word that has changed is we've switched from being in a plane to being in space. So we still have our given point. We still go out our set distance here from that point, and but this time, since we're in space, we can go out that set distance in all dimensions, all three dimensions, and so we get a sphere. So let's talk about spheres. So before we get there, I want to define this new term. It's called a great circle. And a great circle is a circle that's on the surface of the sphere, and it has the same center and the same radius as the sphere. So you see, here's a drawing of a sphere, and these two circles are not great circles. And you can tell because they don't have the same center as the sphere itself, and they also don't have the same radius. But this is a great circle right here. And so if you think about maps, the lines on a map, some of them are great circles and some of them aren't. The equator, that's a great circle. But that's the only line of latitude that is a great circle. Every line of longitude is a great circle. You see how all the lines of longitude, they have the same radius as the sphere itself, and they have the same center. And one of the reasons why great circles are important to us is it turns out on a sphere, the shortest distance between any 2 points, so for example, this point here in northwestern Washington state, and this point here in Europe, like in maybe that's France, the shortest distance between any 2 points on a sphere is the path along the great circle that goes through those 2 points. And this is a little tough, I think, for kids to understand because when we look at our flattened maps and we look at, say, the path between Washington, D.C. and Madrid, Spain, and you draw the quote-unquote straight line, it looks like this would be the shortest distance. But it isn't. It's actually this curved distance because this curved distance follows the great circle path between those two cities. And the reason why I think this is confusing is if you remember from your middle school geography classes, when you flatten a sphere, when you flatten a map, you distort the picture. And so, when we flatten this map, it looks like certain regions are much bigger than they really are. For example, Alaska looks massive. It's a big state, but it's not as massive as it appears on a flat map. So if you're ever flying or traveling and you look at the path your plane takes, it might kind of alarm you to see it's going in an arced path, but it's actually taking the shortest path possible between those two regions. Anyways, we bring up great circles because of this. The formula for the surface area of a sphere, it turns out, is 4 pi r squared. And what that's saying is it takes 4 great circles to entirely cover the surface of a sphere. And when you get to calculus, you'll learn another way to find the surface area and volume of a sphere, but I thought we could talk a little bit about how, if we take this as a given, that the surface area is 4 pi r squared, how on earth do we come up with this formula for the volume of a sphere? Well, if you take a look at a sphere, what you could do is you could cover that sphere, you could, well, not cover it, but you could cover that sphere in a series of pyramids. And like a disco ball, you see these little square bases. Those could act like the bases of a pyramid, and all the pyramids could meet right down here at the very center of the sphere. And so we could say the volume of a pyramid is 1/3 base times height. So the volume of the sphere would be basically the volume of all the pyramids that we use to fill up this entire sphere. Well, if the volume of a single pyramid is 1/3 the base times the height, and the volume of the sphere is the volume of all those pyramids, then we could say that this is really 1/3 times all the bases times the heights. Well, let's talk about that a little bit. That's 1/3, and all the base areas is just the surface area of this sphere times the height. Now, do you see that the height of this pyramid right here is the same as the radius? And so if we substitute in our formula for the surface area, we get 1/3 times 4 pi r squared times the radius, and that's where the 4/3 pi r cubed comes from. And one thing you'll notice is this is our very last volume problem, and it's the easiest of all formulas. I mean, the only thing you need to know to find the volume of a sphere is the radius. So let's take a look at 3 examples and see how we do with those. All right, so here we go. Example 1, find the volume. So here's a sphere, and we have our formula. And in your homework tonight, I want to see each and every part written out like we always do. So start out by writing the formula you're going to use. Now, I tried to trick you. This 16 is not the radius, it is the diameter. So we're going to use 4/3 times pi times 8 cubed. And I'd like your answers 2 ways, please. I'd like it using the number pi. So 8 cubed times 4 divided by 3 is 682.67 pi. And I'd also like you to write it as a full decimal where you type in the pi button in your calculator. And of course, our label is inches cubed. So let's try another one. I'm going to make this one a little bit more challenging. How about the volume of this? Now, to understand this picture, this is not a full sphere. It's a sphere that's been sliced. We call that a hemisphere. So if the volume of a sphere is 4/3 pi r cubed, and we're not dealing with a full sphere, we want to multiply that by a half. So it's really 2/3 pi r cubed because we're just halving the formula. We're just cutting it in half. Of course, half of 4 is 2. And the radius here is 12, so we'll put that 12 in. And again, we'll write our answer 2 different ways. Well, one last problem to take a look at, and this one's pretty tricky. So let's see how this one works. The last problem is, oh my goodness, look at that. What is going on here? Well, you might notice that this is a hemisphere. It's a hemisphere. It's not a full sphere, but I've sliced out a little 3-dimensional sector. And that sector slice is a 40-degree slice has come out of that whole entire hemisphere. So we know the volume of a hemisphere is 2/3 pi r cubed. So it's 2/3 pi times 10 cubed. But that's for an entire hemisphere. I've taken this slice out. So I've taken out a 40-degree slice. So if a 40-degree slice has come out, how much of that entire sphere is left? Well, I'm going to argue we're going to want to multiply that by 320 out of 360. There's 360 degrees in a whole circle, and we've taken 40 degrees out of it. So I need that scalar out in front. And when you do the multiplication, boom, that's what you get. So tonight you have a mix of problems. You have some spheres, some hemispheres, but you also have pyramids and cylinders and prisms and cones. So I want to remind you that each and every problem, I want to see the formula, the numbers you're plugging in, and the answer. Have fun.